Hello everyone, this is Kalpana here. In this video, we are going to solve a differential equation using variation of parameters method. So let's get going. Problem: solve dy by dx plus x sine 2y equal to x cube cos square y using variation of parameters method. So we are given a differential equation of order 1 which is not linear. Given differential equation, dy by dx plus x sine 2y equal to x cube cos square y. Consider the given equation as equation number 1. Now, we'll reduce this equation to linear equation. Okay, so that just divide both sides of the equation with cos square y. Then we'll get 1 by cos square y into dy by dx plus x into sine 2y by cos square y equal to x cube cos square y by cos square y. Right? Here cos square y gets cancelled and we can write 1 by cos square y as secant square y into dy by dx plus x into, since we know that reciprocal of cos theta equal to secant theta and sine 2 theta equal to 2 sine theta cos theta, right? So we'll replace sine 2y with 2 sine y cos y, and we can write cos square y as cos y into cos y, so that 1 cos y gets cancelled from the numerator and the denominator. Then okay, equals to x cube, right? This gives us secant square y into dy by dx plus x, or 2 into x 2x into sine y by cos y equal to x cube. Since sine theta by cos theta equals to tan theta, so we can replace sine y by cos y with tan y. Then this becomes secant square y into dy by dx plus 2x into tan y equal to x cube. Right? Now let tan y equal to some t, because we are going to reduce the given differential equation to linear equation. Okay, let tan y equal to t, or t equal to tan y. Now we need to find derivative of t with respect to x. So here we are going to use chain rule. Dt by dx equals to dt by, since t is a function of x, function of y, right? So we'll use dy. Now let's find dt by dy. Okay, if t equals to tan y, differentiate on both sides with respect to y. We'll get dt by dy equal to derivative of tan y with respect to y is secant square y, right? Now this becomes dt by dx equals to dt by dy, which is secant square y into dy by dx, right? Or if t equals to tan y, then we'll get dt by dx equals to derivative of tan y is secant square y into inner derivative of y with respect to x, dy by dx. You can just write directly like this, or you can use chain rule. Finally, you'll get dt by dx equals to secant square y into dy by dx from this. Okay. Now the above equation becomes, since t equals to tan y, then dt by dx equals to secant square y into dy by dx. Then this equation, the above equation becomes secant square y into dy by dx can be replaced with dt by dx. So you'll get dt by dx plus 2x into tan y can be replaced by t equal to x cube, which is linear in t and x, right? Consider this equation as equation number 2. We have reduced the given differential equation to linear equation. Right? We all know the differential equation which is linear is of the form dy by dx plus some p into y equal to q, where p and q are functions of x, right? Here we have linear equation in y, okay, where p and q are functions of x, right? P equals to 2x and q equal to x cube. So we have reduced the given differential equation to linear equation. Let's now write the homogeneous equation of equation 2. The homogeneous equation of equation 2 is dt by dx plus 2x into t equal to 0, right? Let's now separate the variables by sending the second term to RHS. Then we'll get dt by dx equals to minus 2x into t. Now bring this t to LHS and take the differential dx to RHS. Then we'll get 1 by t dt equal to minus 2x dx. Now the variables are separable. We can perform integration. Integral 1 by t dt equal to minus 2 integral x dx. This becomes log t equal to minus 2 integral x dx is x square by 2 plus some constant, say c. Since we are having one term in terms of log, so let's write the constant in terms of log and cancel this 2. We'll get log t equals to minus x square plus, I'm writing the constant as log c. Now I'll bring this log c to LHS, then I'll get log t minus log c equal to minus x square. Since we know that log a minus log b equal to log a by b, right? So we can apply this formula here. We'll get log t by c equals to minus x square. And consider this equation, homogeneous equation, as equation number 3. Now this becomes t by c equals to e power minus x square. Then t equal to c into e power minus x square, right? Therefore t equal to c into e power minus x square is the solution of equation 3. Okay, t equals to c into e power minus x square is the solution to equation 3. Now, using the solution of homogeneous equation, we'll write the general solution of the given equation. Okay, so let t equal to, just replace the constant or parameter with function of x a into e power minus x square be the general solution of 1. Okay, where a is a function of x, right? So here we need to find a. So a e power minus x square is general solution of 1. T equals to a e power minus x square is solution of 2. But here we are having dt by dx also. So we can say that t equals to a e power minus x square satisfies equation 2, and we need to find dt by dx also. Later we will substitute t and dt by dx in equation 2 to find, so that we will get a. We have t equal to a e power minus x square, right? Let's find t dash. T dash equals to a e power minus x square whole dash. Here t dash is nothing but derivative of t with respect to x, equal to, we will get a dash into e power minus x square plus a into d by dx of e power minus x square, or e power minus x square whole dash. Okay, now let's find derivative of e power minus x square using chain rule. Okay, let sum p equal to e power minus x square, okay, and q equal to this minus x square. Then we'll get p equal to e power q, right? Here we are going to apply chain rule again. dp by dx equals to, since p is a function of q, right, because we are having p equal to e power q, so we'll use differential dq also. We'll get dp by dq into dq by dx. E power q, let's differentiate on both sides with respect to q. Then we'll get derivative of p with respect to q equal to derivative of e power q with respect to q. Then we'll get dp by dq equal to derivative of e power q with respect to q is e power q. So we got the value of dp by dq. Now let's find dq by dx. So we need to differentiate both sides with respect to x. d by dx of q equal to d by dx of minus x square. This gives us dq by dx equal to derivative of minus x square with respect to x is minus 2x. Then derivative of p with respect to x becomes derivative of p with respect to x equals to dp by dq, which is e power q, into dq by dx, which is minus 2x. Now replace this q with minus x square. Then we'll get dp by dx equals to e power, just replace this q with minus x square, then you'll get e power minus x square into minus 2x, right? Or if p equal to e power minus x square, if p equal to e power minus x square, then differentiate on both sides with respect to x, we'll get dp by dx equals to derivative of e power minus x square with respect to x is e power minus x square into inner derivative, that is derivative of minus x square with respect to x, okay, which gives us e power minus x square into derivative of minus x square with respect to x is minus 2x. You'll get the same thing. Instead of using chain rule, you can just go like this, okay? Since d by dx of e power minus x square equal to e power minus x square, that is derivative of e power minus x square is e power minus x square into inner derivative, derivative of minus x square is minus 2x, okay. If p equal to e power minus x square, then dp by dx is e power minus x square into minus 2x. I hope you'll understand. Now coming to the equation. This becomes a dash e power minus x square plus a into derivative of e power minus x square is minus 2x into e power minus x square. This gives us a dash e power minus x square minus 2a x e power minus x square. Therefore, dt by dx equals to a dash e power minus x square minus 2a x e power minus x square. We are having t equal to a e power minus x square and dt by dx equals to a dash e power minus x square minus 2a x e power minus x square, right? Let's substitute dt by dx and t in equation 2. We have t equals to a e power minus x square and dt equals to a dash e power minus x square minus 2a x e power minus x square. Let's substitute these two in equation 2. Substitute, and we have equation 2 dt by dx plus 2x into t equal to x cube, right? Let's substitute t and dt by dx into, it gives a dash e power minus x square minus 2ax e power minus x square plus 2x into t a e power minus x square equal to x cube. This gives us a dash e power minus x square minus 2ax e power minus x square plus 2ax e power minus x square equal to x cube. Here minus 2ax e power minus x square and plus 2ax e power minus x square gets cancelled and we'll get a dash e power minus x square equals to x cube, right? From this we'll get a dash equals to x cube by e power minus x square, or we can write e power minus x square as 1 by e power x square, right? Equal to x cube. We'll get a dash equals to x cube into e power x square, right? We can just write e power minus x square as 1 by e power x square. Then we'll get x cube by e power minus x square can be written as x cube by 1 by e power minus x square. Okay, sorry, e power x square. This gives us x cube into e power x square, or we can just take this e power x square to RHS and we'll get directly a dash equals to x cube into e power x square. Therefore, a dash equals to x cube e power x square. Now we can find a using this a dash. We have a dash equals to x cube e power x square. A dash is nothing but derivative of a with respect to x equal to x cube e power x square, right? Let's now separate the variables by taking differential dx to RHS. Then we'll get dA equal to x cube e power x square into dx, right? Let x square equal to some v. Now differentiate on both sides with respect to x. We'll get 2x equals to dv by dx, right? Or 2x dx equals to dv, or x dx equals to 1 by 2 into dv. Okay. Now we can just split this x cube as x into x square in order to replace x square with v and x dx with 1 by 2 dv, right? So we'll write this as x square e power x square into x dx See, here the variables are separable, okay? Variables are separable. Now we need to perform integration. Okay? dA equals to, just substitute or replace x square with v, we'll get v into e power v into x. Dx can be replaced with 1 by 2 dv. Now apply integration. Integral dA equals to 1 by 2 integral v e power v dv. Okay? Or consider this v as capital V, because I'm going to use a formula which needs small u and small v, so that I am changing it to capital V. Okay? Fine. We know that integration by parts formula integral u dv equal to uv minus integral v du, right? Here we are having integral v into e power v dv, polynomial function, that is integral v into e power v dv. Here integrand is of the form product of polynomial function into exponential function. Let's consider polynomial function as small u and the remaining part as d small v. Okay, u equal to capital V and dv equals to e power v dv. Okay, just differentiate with respect to capital V, then we'll get du by dv equals to derivative of capital V with respect to v. From this we'll get du by d capital V equals to derivative of v with respect to v is 1. From this we'll get du equal to d capital V. Okay, and here we'll integrate on both sides. We'll get v equal to e power v. Now just use this formula, then we'll get integral u dv equal to utilize this formula, we'll get integral u, which is v into dv, e power v capital V dv equal to u into v, u is capital V, into small v equal to e power v minus integral small v, which is e power v into du, du is dv. We'll get v e power v minus integral e power v dv is e power v, right? Or we can write it as v minus 1 into e power v. Okay, this becomes integral dA equal to a equal to 1 by 2 into integral v e power v dv is v minus 1 into e power v plus integral constant, say some c1. See, if you are confused with v e power v dv, let's try using x. Okay, now consider the polynomial function as u and the exponential function into dx as some dv. Okay, where u equal to x and dv equal to e power x dx. Here we'll differentiate on both sides with respect to x. Okay, then we'll get derivative of u with respect to x is du by dx equals to derivative of x with respect to x is 1. From this we'll get du equal to dx. Here integrate on both sides and we'll get integral dv equal to integral dx d. From this we'll get v equal to e power x. Now we can apply this formula. We'll get u into v. U is x into v is e power x minus integral v which is e power x into du is dx. From this we'll get x e power x minus e power x, which gives us x minus 1 into e power x if we take e power x common from these two terms. Okay, we got the same thing. Okay, no need to get confused with v, p, q, everything. Now we have a equal to 1 by 2 into v minus 1 into e power v plus c, right? I mean c1. Let's replace capital V with x square, since capital V equal to x square. Then this becomes a equal to 1 by 2 into v, which is x square minus 1 into e power v plus c1, or a equal to 1 by 2 into x square minus 1 into e power x square plus c1. Therefore, a equal to 1 by 2 into x square minus 1 into e power x square plus c1. So we got a. Let's now write the general solution of the given equation using t equal to a e power minus x square. Simply substitute t and a in this. We have t equal to a e power minus x square, right? So the general solution of equation 1 or given equation is obtained by substituting t and a in the above equation. Right, then we'll get, just replace t by tan y, since t equal to tan y, and a equal to 1 by 2 of x square minus 1 into e power x square plus c1. Just substitute these two in this equation, then we'll get t, which is tan y equal to a 1 by 2 of x square minus 1 into e power x square plus c1 into e power minus x square. This gives us tan y equal to 1 by 2 x square minus 1 into e power x square into e power minus x square plus c1 e power minus x square. Then this becomes tan y equal to 1 by 2 x square minus 1 into, here we are having e power x square into e power minus x square, right? Either we can add the powers, then we'll get, sorry, it's minus, right? E power 0, since e power 0 equals to 1, or we can just write e power minus x square as 1 by e power x square, where e power x square gets cancelled, we'll get 1, right? So we can replace e power x square into e power minus x square by 1, we'll get 1 here, plus c1 e power minus x square. This gives us tan y equal to 1 by 2 into x square minus 1 plus c1 e power minus x square, which is the required solution of the given equation of order 1. Therefore, tan y equal to 1 by 2 into x square minus 1 plus c1 e power minus x square is the required solution. This completes the problem. So we have seen a problem from variation of parameters in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.